Welcome to CD Bioparticles channel. In this video, we'll present you an overview of magnetic beads-based chemiluminescence immunoassay. Immunology was established in the 18th century with the study of microbiology and entered the development period from the 19th to the middle of the 20th century. During this period, the general understanding of the immune function in the scientific society has changed due to the shift from observing human phenomena to conducting experiments. The period of modern immunology began from the middle of the 20th century. Immunoassay is based on the specific reaction between antigen and antibody, and the detection signal is amplified and displayed by isotopes, enzymes, chemiluminescent substances, and so on. It is often used to detect proteins, hormones, and other trace substances. The market offers a range of well-established classical detection methods that are conveniently packaged in kit form. These include radioimmunoassays and enzyme-linked immunosorbent assays. These two detection methods were highly sensitive and suitable for a variety of biological and chemical testing applications. While RIAs are highly sensitive assays, they are comprised of highly hazardous, radioactive reagents, which presents a significant safety risk. The handling and disposal of RIA refuse can present challenges in regulated laboratory environments and may also be costly. ELISAs are a more environmentally friendly alternative. However, ELISAs lack the dynamic range of RIAs and are not as sensitive when an analyte is present in very low concentrations. Furthermore, ELISAs often require a lengthy process, with a final reactive step necessitating the use of a stop reagent to prevent the color of each test well from continuing to develop. A new, faster technique has been developed which has transformed the field of biological and chemical detection. Chemiluminescent immunoassays, short for CLIAs, are based on the detection of a protein that emits light in a chemiluminescent reaction. No stop reaction is required, and incubations are short. CLIAs have a much wider detection range than either RIAs or ELISAs and are also extremely sensitive under low analyte concentration conditions. Chemiluminescent immunoassay was developed in the late 1970s. The principle of this technique is to use the free energy released by the chemical reaction to excite the intermediate from the excited state to the ground state, commonly used alkaline phosphatase amantadine amine and horseradish peroxidase luminol derivatives. During this process, equal-level photons are released, and the quantitative analysis is accomplished by measuring the photons. CLIA is a very excellent quantitative analysis method. It has the specificity of fluorescence. At the same time, it does not need the excitation light, avoiding its stray light from interfering with the analysis and improving the sensitivity. Moreover, CLIA avoids environmental pollution and health hazards caused by radiation analyses. CLIA is a highly sensitive technique, making it an ideal choice for a variety of applications. CLIA is capable of determining all antigenic substances, including semi-antigens. In the 1990s, CLIA began to demonstrate the following characteristics. Firstly, high sensitivity, with a limit of 10 to the negative 17 to 10 to the negative 21 mole per liter, which is significantly higher than that of RIA and ELISA. Its sensitivity is comparable to that of the time-resolved fluorescence immunoassay, while offering a more cost-effective solution. Secondly, offers strong specificity and good reproducibility. The coefficient of variation is less than 10%. Thirdly, the determination range is extensive, spanning up to 7 orders of magnitude. Fourthly, the reagent is stable and free from contamination for a period of 12 months. Last but not the least, it is straightforward to operate and can be automated. Magnetic beads-based CLIA is a well-established and straightforward technique that integrates magnetic separation technology, chemiluminescence technology, and immunoassay technology. This technique fully leverages the rapid and straightforward automation of magnetic separation technology, the high sensitivity of chemiluminescence technology, and the specificity of immunoassay. It is an indispensable tool in the field of biological analysis. To further enhance the sensitivity of chemiluminescence detection, immobilizing enzyme-labeled antibodies on nanoparticles can increase the number of antibodies bound to a single antigen, amplifying the signal. The principle of chemiluminescence detection varies. First, the indirect method. The indirect method involves coating the antigen on magnetic beads and utilizing enzyme-labeled anti-antibodies to detect antibodies in samples. This approach is particularly suited to antibody detection. This method offers a convenient solution. By simply modifying the coating antigen, it is possible to detect a range of different analytes. However, the specific antibodies in the markers may compete with the antigens, potentially leading to false negative results. The capture method. Specific IgM and specific IgG for certain antigens are often present in serum simultaneously, and the latter can interfere with the detection of IgM antibodies. Therefore, the capture method is often used to determine IgM antibodies. All serum IgM, including specific IgM and nonspecific IgM, are immobilized on the solid phase, and the specific IgM is determined after IgG is removed. The solid phase antigen competitive method. The competitive method entails the competitive binding of tested antibodies and enzyme-labeled antibodies to the antigen on the surface of the magnetic beads. The quantity of enzyme-labeled antibody bonded to the solid phase carrier is inversely proportional to the amount of antibody present in the sample. In the absence of antibodies in the tested sample, the enzyme-labeled antibody can bind to the antigen effectively, resulting in a strong signal. In the event that antibodies are present, the competitive binding between the enzyme-labeled antibody and the antibody in the sample to the antigen will result in a reduction in the binding power of the enzyme-labeled antibody to the antigen, as well as the signal intensity. The sandwich method. The sandwich CLIA is a detection method that combines the double antibody sandwich method with the chemiluminescence method. The first step is to pre-coat the microtiter plate with specific antibodies conjugated to magnetic beads that are targeted against the analyte. Subsequently, the standard or sample is added to the microplate wells, where it will bind to the immobilized antibody present in the wells. The next step is to add the biotin conjugated antibody, which will bind to the analyte adsorbed on the plate. The complex of two antibodies and the analyte in the well forms a sandwich structure. Once the free biotin-labeled antibody has been removed and avidin-labeled horseradish peroxidase has been added to each microtiter plate and incubated, luminol is added for quantitative analysis. When it comes to choosing the right magnetic beads for your CLIA, the material plays a crucial role. Let's break down the pros and cons of a few common types. Magnetic silica beads. These are quite sturdy and chemically stable. However, they can absorb a lot of water, making reactions more complex. Plus, they don't do well in alkaline conditions. Magnetic polyacrylamide and polyacrylic acid beads. They're great with water and blood, and you can even tweak their properties by mixing them with other materials. But they have a tendency to shrink. Magnetic polystyrene beads. These are tough, easy to customize, and can handle strong acids and bases. However, they're naturally hydrophobic, so you'll need to add something to make them stick to proteins. The best choice for you really depends on your specific needs. For instance, if you're working with a protein that doesn't like hydrophobic surfaces, polystyrene might not be the best option. Let's talk about the different types of magnetic beads we can use for your CLIA. These beads come with various functional groups that act like little hooks, helping us capture specific molecules. For example, if you have a molecule with an amino group, we can use beads with either hydroxyl, carboxyl, or N-hydroxylsuccinimide activated groups. These groups act as binding partners for the amino group. Or, if you're dealing with a molecule with a sulfhydryl group, epoxy-activated beads would be a good fit. And then there's streptavidin. It's like a super strong magnet for biotin. So, if you can label your target molecule with biotin, streptavidin beads will pull it right out of the solution. Choosing the right bead depends on the specific molecule you're targeting. How to choose the perfect magnetic beads for your CLIA. Think of these beads as tiny magnets with special coatings that can grab onto specific molecules. What we're looking for in a great magnetic bead. Speed. We want these beads to respond quickly to a magnet so we can separate them from the rest of your sample. Consistency. Every bead should be the same size and shape. This makes our results more reliable. No sticking. We don't want the beads sticking to anything they shouldn't. This keeps our results clean and accurate. Toughness. These beads need to be able to handle different conditions without falling apart. A good match. The coating on the bead has to be a perfect fit for the molecule you're trying to catch. So, what are we looking for in your specific CLIA? What kind of molecule are you working with? What size is it? And what conditions will it be in? Once we know these details, we can pick the perfect magnetic bead for your project. CD Bioparticles offers a comprehensive range of magnetic beads for chemiluminescence immunoassay that can specifically and efficiently capture and detect target molecules, making it an invaluable tool for diagnostic and research applications. For instance, Our carboxy magnetic particles for CLIA allow customers to align different systems and different targeting assays. These particles possess a number of beneficial characteristics, including magnetic properties, a rapid response time, a high density of carboxyl functional groups, a well monodispersed and submicron particle size, and the ability to covalently conjugate with peptides, proteins, oligonucleotides, and other biological ligands to the surface of microspheres under the action of special chemical reagents. It is an invaluable tool for medical and molecular biology research. For more information, please visit our website, www.cd-bioparticles.com.